So the topic we're going to begin discussing today are generic algorithms in STL, and we'll see what they do and how they work. Keep in mind that in STL, all the algorithms operate over iterators rather than containers. And that's by design, and we'll talk more about that in a second. So you can see here we have the copy algorithm, which is one of the favorite ones I like to talk about as an example because it's really simple and it's very fundamental to all things STL. And you can see down here that when you copy something, you don't pass in the vector, you don't pass in the dec, you pass in the iterator range you want it to work on. And the reason for doing that, of course, is that way we can have one algorithm that'll work for any type of container, even if it's an associative container, even if it's an unordered associative container, even if it's an array, you can use all those kinds of things, and they all work over iterators, which gives a lot more flexibility and reuse to the code. To make this work, every container declares an iterator and a const a const iterator and other traits that describe what the capability is of this particular iterator. So here's this particular container. So here you can see a vector. This is a snippet of a vector implementation that is representative of what you might find in your own STL that you have on your C-line IDE, whether you use Clang or GCC or G++ or whatnot. And you can see here how we take the types that are passed in to the vector template class, and then we use them to make our traits. So value type is a type def of the type T that's passed in as a parameter to the template. Allocator type is the allocator that's passed in. And then you can see how we use various traits from the allocator type in order to be able to get other traits that we're going to use for our vector class or for the implementation of vector. And this also illustrates the use of this thing called normal iterator. And that's the way that a lot of the C++ implementations will implement their iterators. They don't have a separate iterator for every class. They have this thing called normal iterator, and then they parameterize that and then make iterators for each of the classes. So that's pretty cool and a great example of reuse. Speaking of reuse, one of the things you'll discover as you're doing assignment number 4 is that once you get your iterators working, you can go back and clean up the implementation of all your other code quite a bit. And it should become much, much simpler once you do that, because you no longer have to do all the, scoped array.get plus size kind of gobbledygook in your implementation of the array class, but instead you push that gobbledygook into the implementation of the iterator. And it's kind of like, hiding. You ever play one of those games with the cups where you're trying to see, where's the quarter? What cup is the quarter under? You're trying to hide it. Well, that's what we're doing with complexity with STL. We're hiding the complexity in the iterators, thereby making the implementation much, much simpler. And that is a very, very good design choice when you use STL. As you can see, certain containers like lists and maps and sets and multi-maps and multi-sets, and then of course things like unordered multi-map and unordered set, etc., they all define bidirectional iterators. And that is intentional, and that's because those data structures don't support efficient random access. So with a list or a map, you can't just sort of jump into the middle. You have to iterate there from one side or the other to get to where you want to go. So they make bidirectional iterators, which as you'll see as you implement your random access iterators for assignment number 4, there's a lot of things you got to think about to implement a random access iterator, a lot more complexity. And that works fine for things like arrays or vectors, which are very simple structures. For a list or for a multi-map or an unordered set or whatnot, doing that kind of stuff would be very complicated and really inefficient and give you the wrong impression about what kind of capabilities you actually have with that type of container. So those are defined as bidirectional iterators, and that means you have a lot less to implement if you're implementing the operations on a bidirectional iterator. You can leave off all the stuff like plus equal and minus equal and plus and minus and subscript and all that good stuff, all of which, of course, you'll have to implement for assignment number 4. Vectors and decs are random access iterators. So that provides the full-blown, all features on deck kind of capabilities that we've come to know and love for those types of containers. So once again, the goal is to try to have these different categories so that depending on what your algorithm requires, depending on what your container can support, you only have to implement the minimum set of capabilities, and then you can kind of mix and match within those categories. Each container defines a bunch of factory methods for its iterator types, should be plural. And here are the typical spate of factory methods that are defined in modern containers. You, of course, have begin and end, and those give you back iterators, unless you have a const object, in which case they give you back const iterators. Then there's also cBegin and cEnd, which you can use in more modern versions of C++ in order to be able to say, I want a const iterator even though I'm a non-const object, because I'm not going to be writing to anything. I don't want this to be written to in any way, shape, or form. And then there's also the corresponding R or reverse factory method. So rbegin, rend, crbegin, crend, and they, of course, return reverse iterators to the underlying container. And we've talked about reverse iterators. They're really quite simple. In fact, if you look at the implementation, you can see that a reverse iterator is just an iterator that has reverse iterator wrapped around it. So once again, STL has tremendously powerful reusable abstractions that it itself applies in order to simplify the implementation of STL. So that's what people sometimes talk about is eating your own dog food, which is a somewhat whimsical and memorable phrase. Not sure why you would want to eat your own dog food, by the way, even if you have tasty dog food, because dog food's made for dogs, not for people. But the point is that I guess another way to say it is practice what you preach. If you're trying to tell people to go out and implement reusable abstractions, then by all means, you should do that when you write your own code that people can use as the basis for reusable abstractions. Okay, composing an algorithm with a container, connecting them together is just about invoking the algorithm with iterators to that container. And once again, we revisit our copy algorithm and our vector, and you can see just how ridiculously easy it is to do this. And why this works so well in STL and really the perfect storm of beautiful combinations of features was the introduction of templates in the early 90s into C++, which then allowed the people who'd been working on these generic algorithms, Alex Stepanoff and Dave Musser and so on, to move their attention from a language like Ada, which also has a form of generic capabilities, not as powerful as C++ templates, but sort of along the same lines. They were able to move all the stuff that they developed for Ada over to C++ very readily, and we ended up with the STL. And what's cool about this is it's compile time, type safety for containers, for iterators, and for algorithms. And that's very valuable because, number one, it's really hard to get type errors where you put a square peg in a round hole or try to put a square peg in a round hole. And number two, it allows for enormous amounts of compiler optimization under the hood, which is what leads to this amazing zero cost abstraction or zero overhead abstraction principle that Bjorn Strustrup and others like to talk about so much in C++. Well, it turns out that there's 4 different ways to categorize STL algorithms. And what I'm going to do is I'm going to quickly summarize them now, and then we're going to go back and start talking about examples of such algorithms in each of the categories. So the first type of algorithm category is called non-mutating algorithms. And these are algorithms that operate using a range of iterators, but they don't make any changes to the data elements found. So you can think of them as basically sort of read-only or const-style iterators. And we'll see a whole pile of these things. You've already been exposed to some of them through other discussions that we've had, stuff like count or countif or find if not, all that good stuff. And those are all examples of algorithms that don't make any changes under the hood. There's also a bunch of mutating algorithms. And as the name suggests, they change something about the data elements. They change the order, they change the contents, they do something to the underlying elements in the container that they're iterating over as they're doing their thing. And we've also seen a whole pile of these as well, things like copy, of course, and transform, fill, These are all examples of mutating algorithms that make changes. Then there's also a bunch of algorithms that deal with sorting and sets, which, of course, both of those things could be considered mutating, but we tend to pull them out and talk about them separately. So sorting deals with sorting, and there's a bunch of sorting algorithms in STL, including sort, which is the most common sort, but there's also other types of sorts as well. And then there's a bunch of set algorithms, and you can do various things with sets. And then the final type of algorithm are the so-called numeric algorithms, which are mutating algorithms that produce numeric results. And we'll see that in the discussions when we go through this stuff, I kind of lump numeric in the same pile of discussions as sorting and sets, but that's primarily because there's only a handful of numeric algorithms that we're going to talk about, so they don't go into as much detail. So within these categories, there's also another type of differentiation of algorithms, and these are the ones that have the if suffix. And what they do, we've seen these again, find if, count if, and so on. And what they do is they take some kind of predicate functor or lambda function, and they will be used to check something. You're not just comparing against a value like the value 5, you're comparing against a predicate. So you can do things like greater or less or equal to in a relational style way. And so predicates give you much more open-ended ways of doing checks and doing various computations that don't fit nicely into a single value. And of course, the predicate returns true or false, and that's what drives the behavior of the algorithm. We often use these predicates with functors and functor calls and binders and negators and all that kind of good stuff. So here are some very simple examples where we've got a vector of ints and a list of ints, and we can do find if on the vector, checking for things that are greater than 5, for example. We can do find if on the list, checking for things that are not greater than 5, and real simple mixing and matching of various types of function adapters. Or we can throw the function adapters out the window and just use lambda functions directly. So it's kind of up to you to decide how you want to drive this stuff. So let's finish up the discussion of STL by giving a brief overview of why this is good, and then we'll launch into lots of examples. So one of the cool things about STL is they decouple the containers they operate on, and they don't actually know anything about the containers. They only know about iterators. So all the containers with the same iterator type can use the same algorithms. So here you can see that we've got copy being used on a vector. And it's also trivially easy to have copy that works on a list or on an array and so on. And therefore, you don't have to keep rewriting these things over and over again. You just have to write it once and you can reuse it. And that basically helps to minimize the amount of code that you have to write. So you can write, find or count or transform one time and then reuse it.